All right, so this is the Secure Container Group. My name's Jacob Cooley.
My name's Trey Curtis.
My name's Luke Jensen.
I'm Damian Pullman.
And I'm Mark Reininger. So back in September, Los Alamos came to us with the goal to design and build a secure container. Essentially, they wanted a metal vessel to store and transport various objects in a secure manner. This container needed to satisfy several requirements. First of all, it had to be 30 gallons in volume, had to be 55 pounds dry weight, and to not exceed 110 pounds loaded. It also had to withstand pressure and temperature changes, and most of all, it had to comply with 49 CFR 178 subpart M, which is basically a standard of requirements for non-bulk packaging. And this standard lays out specific criteria for a container of this nature, specifically that it has to withstand pressure changes to a certain degree. It has to seal against specific environmental conditions, and it has to withstand impact testing, specifically its ability to remain structurally sound after impacts and collisions. In addition to these requirements, Los Alamos also wanted the container to be secure and to lock. The locking was carried out by two independent locks, one mechanical and one electromechanical. Preferably, these two were combined into one locking mechanism on the container itself. In addition to these requirements, Los Alamos also listed some required characteristics. Specifically, it's ergonomically friendly, easy to use, portable, easy to manufacture, and cost effective. And here's Damien with the design.
All right, so our container was designed to incorporate a rotating locking ring, which is used to supply the downforce to the lid and keep the container sealed. The locking ring is prevented from rotating by using a linear solenoid, which is housed in the lock boxes that are welded onto the side of the container. And this solenoid is controlled using a keypad. When the correct combination is entered into the keypad, the solenoid will actuate, which allows the locking ring to be rotated, and then the lid can be opened. So the locking ring will constitute the mechanical locking method, and the solenoid is the electromechanical locking method. So we started with a standard 30-gallon drum for our lock prototype, as the lock was the main focus of this project. So the ring originally used a nut and a bolt to seal the container, but we modified this to incorporate a rotating locking mechanism. The ring, or the container and the ring, were both notched, which allows the lid to be set in place on top of the container. And the remaining protruding tabs on the ring itself are what provide the sealing force once it's rotated into the lock position. The sealing gasket is housed inside the lid. However, the lid and the ring are not actually fixed together, but they are in one assembly. So when you place this assembly on top of the container, the lid and the gasket will remain stationary, and only the locking ring can rotate. So once this ring is rotated into the lock position, the spring-loaded solenoid will protrude into the lock box on the lid, and this automatically locks the container. When you want to open the container, you just put in the combination into the keypad, the solenoid will retract, and this allows you to rotate the lid, and then the container can be opened. So the container was designed to minimize the weight of the lid, just to keep up with user friendliness. You don't want a heavy lid, and also to have the lid flat. If additional containers were produced, they would allow for easier stacking. So we decided to incorporate the electronics, the keypad, the solenoid, the battery, etc., into the lockbox housings, which are on the container itself. The handles, which are attached to the lockboxes, by using a metal tube and a through bolt. The bolt applies a clamping force between the tube and the two bars, which are connected to the handle itself. These holes in the lock boxes for the tube are a clearance fit, which allows the handles to rotate freely, and this enables the container to be lifted in a variety of ways. Up next, we've got Luke with simulations.
Yeah, so if you look at the bottom left portion of the poster, I'll be talking about the FEA simulations done there. A total of 5 FEA simulations were performed to simulate the fully loaded weight of the container being applied to the handles as if it were to be lifted using the handles. The loading scenarios simulated were a single handle lift, where as if the entire container were to be lifted by one of the 2 handles. Vertical strap lifting, as if 2 straps were used to lift from the handles, and those straps would be perfectly vertical. Angled strap lifting, where it would be a single strap which is looped through the handles. And then 2 separate weld analyses were performed, simulating the max loading applied to the welds in both the X and Y directions. And that would be the full weight of the container on just one set of welds on one lock housing. The angled strap lifting is the simulation which is presented on the poster because it is the simulation which resulted in the highest stresses and the lowest factors of safety. The angled strap was modeled to simulate a strap being looped through the container handles, and it was coming off at 45-degree angle with a crane lifting the fully loaded container via the strap. Some static analysis was done to determine that in order to hold the 555-pound weight of the container, each handle would be subjected to a 393-pound load force at 45 degrees with respect to horizontal. And this can be seen in the simulation, which is shown. And this force comes from 277.5 pounds, which is half of the maximum weight. And then that amount of force applied at a 45-degree angle would have to be 393 pounds in order to overcome vertical lifting forces, gravitational forces. So if you look at the tables that are presented there were 2 materials that were used in order to construct the handles and the lock box. This is 1026 steel with a yield strength of 60,200 psi, and 1018 steel with a yield strength of 53.7 thousand psi. The max stresses present from the simulations were 15,000 psi. Which resulted in a safety factor of 3.5 for yielding and 4.2 for failure. And as previously stated, the fully loaded container would probably be only 110 pounds, which is the maximum weight for 2 people to carry, as if one person, 2 people were to grab a handle each and simultaneously carry it. But since we used the 30-gallon drum for our prototype, we figured we would build the lock boxes and the handles strong enough to hold the fully loaded weight of the 30-gallon drum along with the additional 55-pound weight of our components. And that's what I have to say about that. So Troy will be next, and he will talk about the functionality.
Yep. So the hardware that we used and the microcontroller was an Arduino Uno. We used this primarily because we had more familiarity with the programming language and all the functions that our Arduino can do. We also like the simplistic design of the Arduino. The Arduino and the solenoid, they ran off of 3 18650 batteries, which would provide enough battery life to last a year for the container. Although we did use a 9-volt battery in testing, and this is mostly because it was easier to maneuver a 9-volt battery, and we were kind of under time constraints, so that was a problem too. We used a 5-volt relay in order to activate the solenoid lock from the Arduino, and we also added a power switch later on that would cut and supply power to the Arduino. That way, we noticed that the Arduino, when it was just not doing anything or just not operating, it was still drawing a lot of current and draining the batteries a lot more fast than we would have liked. So we added that power switch. We also added a piezo buzzer, which would make a buzzing sound each time you pushed a button on the keypad. And that was a nice audio feedback because the first thing we had was a LCD screen, but it drew too much current. The hardware itself, all the All the components were mounted inside the container, as we said before. It was inside the locking box where the handles are. And the keypad itself was secured to the face of the lockbox on one of the handles. And this allowed it just for nice compact, and it was a quick way to put the prototype together in time. So next we got a little demo that shows you how it operates. So sorry for the quality; it's kind of hard with the streaming. But first, we see that we can't open it if the lock is engaged. So we're showing that. And then we turn the power button that's on the bottom side, as you can see, and we input a 4-digit combination. Once that, you would hear an audible click, which signifies that the solenoid is engaged, and you can open it up and twist it off and get inside the container. So that's how it works, and I want to bring you over to Jacob now, who is going to wrap things up.
So moving forward with this, there were some requirements with this prototype that were not able to be met due to some complications and constraints we ran into. So there are a couple things that will need to be done to finish this product. One of the main requirements that needs to be finished is to secure a pressure relief valve. It's a dual wave valve to equalize pressure outside and inside the container. We did some pressure testing initially. We fitted a pressure valve, as you saw in the video. We had a pressure valve on the lid so we could pressurize the container to see where we stood as far as how the seal would hold up. We were able to get up to about a PSI before we started having some issues, so there could be some fine tuning with that. Also, as Troy was talking about the keypad and all that, the wiring for that and the keypad itself will need to be fitted into a waterproof container. Get it waterproof so that it's not out, exposed. And the sanding and painting of the container, as far as aesthetics go, that's something that would probably need to be done as well. The picture on the bottom right, that shows our simulation for our driving range simulation. Essentially, what it is supposed to do is to show that the container was environmentally sealed. So that's what we tested with that. That's as far as we have. That's as far as what we've got for the project. Are there any questions?